I'm out here at a dark site to explain to you why I think an SCT on an alt-az mount is an ideal choice to do electronically assisted astronomy. Now, if you're not real familiar with EAA or electronic assisted astronomy, simply stated, you replace the eyepiece, which you would look through on the telescope, with a camera. And why would you do that? Well, with the camera, you can integrate over many seconds, tens of seconds, even minutes, and you can see much, much more than you're going to see with your eye, because the human eye, as powerful as it is, can only integrate for a small fraction of a second. And the human eye is not good in low light situations like dark skies at night, so you don't really see things in color. But if you choose a color camera, you will see things in brilliant and vibrant color. Now, why do I like an SCT for EAA? Well, when you look at the cost per aperture, you'll find that an SCT is much less expensive than a refractor. Now, that's not to say that refractors aren't good for EAA. They certainly are, and many use them for wide field applications. But when you try to get to fairly large apertures to collect a lot of light, they get prohibitively expensive. Now, for similar sized apertures, Newtonians tend to be less expensive than SCTs, and they're also very good for EAA, especially an imaging Newtonian, which is designed to come to focus with a camera attached where the eyepiece might go. Now, the advantage of an SCT over a Newtonian is its versatility. The SCT's native focal ratio is f10, so that's great for very small objects. For planets, small deep sky objects, you basically can zoom in and see more detail. However, most EAA and most objects are done with a focal reducer. And so here is a Celestron 6.3x focal reducer, which I'm going to use this and show you how to set this up with this telescope later. This will reduce the focal ratio by a factor of 6.3, which then speeds up the imaging by a factor of 2.5. If you have an edge version of one of these, they sell a 7x reducer, and that will speed up the imaging by a factor of 2 compared to f10. Now, if your SCT is fast star compatible, that means the secondary mirror can be removed and replaced with a hyperstar. That will get you down to f2, which is 25 times faster than f10. So just imagine, you can find in seconds or tens of seconds an image that would take you minutes to do at f10. So it's very versatile, working at f10 for small objects, f6.3 or f7 for a majority of objects, and f2 for very wide field, very fast imaging system. Now, this SCT is an 8-inch SCT, and it's on an alt-az mount. It's a Celestron SE mount. So why an alt-az mount? Alt-az mounts do not track the Earth's rotation. They have two axes of rotation. One is in the azimuth, or the horizontal, and the other two is in the altitude. So this will only track the stars correctly if you were at the North Pole, where Polaris would be straight up and the stars would appear to track along the horizon, or the same thing on the South Pole, where the South Celestial Pole would be straight up. Anywhere else, the Earth's axis is tilted at an angle, and so while this can keep a star in the center of the field of view, the stars around that star, if you take too long of an exposure, will appear to rotate around that star. And so alt-az mounts are not really used much for imaging, but they can be used for EAA. And why is that? Well, about 7 years ago, a fella in England, Robin Glover, came out with a software called SharpCap. And the revolutionary thing about that software is it can stack images one on top of the other live while you're taking them and watching the image build up. It takes out the rotation of the stars from frame to frame, and enables you to take essentially much longer total exposures by stacking a bunch of shorter exposures. And I'll give you a demonstration of that tonight when it gets dark. So the other thing to note about SCTs is they are on a alt-az mount. They're actually very lightweight. You can actually carry this from inside your house to your backyard without disassembling. If you want to, you can take off the OTA and you can take the main mount from the tripod very easily, very quick to set up. These are fairly low cost in terms of astronomy equipment. The 5-inch version of the SE is under $1,000. 6-inch is $1,100. The 8-inch goes up to $1,600. And then you have the option of upgrading the mount to Celestron's Evolution mount, which will have better gearing and better tracking in it, but you will pay for that. So the 8-inch version of the Evolution is $2,200, and they also make a 9.25-inch version, which is $3,000. So now you're getting up in price. But we're going to show you what you can do with the 8-inch SCT on an SE mount, and we'll take a look at that tonight with an actual demo. And the next thing I want to show you is how to set up the imaging train. Now, if you want to shoot at f10, you simply remove the eyepiece and its diagonal. You take your camera, and it will typically have a nose piece that is designed to slide in where the eyepiece or the diagonal goes. Then you attach the USB cable, and that cable will go to your PC. Now, the one thing to be careful here is when you are pointing at a high elevation, almost to the zenith, maybe 80 degrees and getting close to 90 degrees, you have to make sure this will clear the base of the mount. And what I've done in this case is I've pushed the OTA as far forward in the mount locking arms as I can, so I can get fairly good clearance. And I'm going to need that when I use this 6.3x focal reducer, because then the telescope imaging train will be much longer than simply attaching the camera to the SCT visual back, which is what this is called. Well, I don't have a Hyperstar for the 8-inch that we're going to use later tonight. I do have a Hyperstar on my 11-inch SCT. So you basically unscrew and take off the secondary, which sounds more scary than it is. Once you get used to it, it's not that big of a deal. I even do this in the dark now. And then you screw on this complicated piece of optics that you can get from Starizona, and it will reduce this from f10 to, depending on which model, f1.9 to f2 to f2.1. And so, as I said, that will give you a much wider field of view and really speed up the optical imaging system. And then your camera screws on the end to that with the appropriate adapter, which Starizona will help you get. And then your cable comes through there. And don't worry about the cable, because it won't really interfere with the light coming in there. So that's the Hyperstar, and it can get pretty expensive. So I'm going to show you instead a much less costly solution, which is still very good, and that's the Celestron 6.3 focal reducer, which is $190. And we'll show you the optical imaging train for that in a moment. So as I said, we're going to use the Celestron 6.3x focal reducer, and this is going to replace the visual back. So we're going to unscrew the visual back, don't drop it, take it off, and then we'll screw this focal reducer in its place. Now, the important thing with focal reducers is to get the right spacing between the optics and the focal reducer and the imaging plane, or the chip, in the camera. And this, I'm going to use tonight this ASI 1600 color camera, and quite a few of these ASI cameras, the chip is 7.5 millimeters back from this front edge of the red part. don't count this. So the correct spacing for these Celestron focal reducers, whether it's a 6.3 or the Edge 7X, is 105 millimeters. So you need to be 105 millimeters back from the flange here, where the threads end, to the imaging plane or the chip. So if we're already 7.5 back here, I just need to build up enough spacers for 97.5 millimeters plus 7.5 will put me at 105. Now, the elegant way to do that is to buy screw-on spacers. Everything will be nice. I didn't have any handy. I have these slip fit ones. These work also. This is an SCT adapter. It will screw on like that. And this is a slip fit here. And so this camera can slide in here with the compression ring. And then all I have to do is measure from this point back, and I want to be to 97.5, and that's right about there. Okay? So what happens if you're too close? If you're too close, you don't get the 6.3x, you'll get maybe 7.5x. If you're too far, you'll get even more focal reduction. So you can play with that. You can use this and adjust the focal reduction. The problem is these are designed for a specific back focus, and that's 105 millimeters. When you get too close or too far, you will get some image distortion around the edges. You'll get vignetting around the edges. But for a lot of people doing EAA, that doesn't matter. They just like to play with this spacing. Now I'll put some links for some of the screw-on spacers like Beta Verilok and others, which you can set up this spacing with all threads instead of any slip fit. But this will work fine. Now the key is when we go to 90 degrees, do we have enough clearance here? And that's why I had to modify this and move this forward to make sure I had enough space here. Some people will put a diagonal on, and they can use the diagonal to come out at a right angle, and you just have to add the optical path length of the diagonal. And I'll put a link to a very good article on cloudy nights where the gentleman examined many different diagonals, and he has data on the optical path length of those. So then you just add that length to whatever additional spacers you need, and the camera will come out at a right angle. So you don't have to push the scope as far forward as I have done. The disadvantage of pushing this so far forward is it's less stable, but it is in there rigidly. The other thing to note is you will not be able to use a cooled camera in this kind of straight through configuration. It's just too big. It will not clear. You can use it with the diagonal at 90 degrees, but not in this configuration. And my camera is not a cooled camera. Okay, so that's basically the optical train for the 6.3x focal reducer. If you had an Edge, you would have a 0.7 focal reducer here, and you would have the appropriate spacers and then the camera on the other end. The next thing to address is the basic setup and alignment of the mount. So to set the mount up, you want to make sure the tripod is level. Use a level, put it on the base, and adjust the tripod legs and make the measurements in two orthogonal directions. I did that ahead of time. I got this fairly level, and I also don't want to extend the tripod legs very far. I want to keep this low to the ground for stability. Since we're using a camera, that won't be a problem for us. We'll be sitting at our computer a few feet away, and we don't have to worry about straining our back to get down here to look through an eyepiece. Now, as I said, I have moved this far forward in the clamps, but I'm making sure that I have enough clamping that this won't come loose. It would be more stable the further back it is, but this will have to do. Now, to power this, you have two options. You can open this part here and you fit in some AA batteries. The nice thing about that is it's all self-contained within the mount itself. The alternative, they do give you a cigarette lighter plug to 5.5 by 2.1 millimeter connector. It plugs in here to supply the, plugs in here. And then there's an on-off switch, and this would go into the battery. What I noticed is when I run this off of the AA cells, the motor is a little less dynamic than it is with the external power supply. So the disadvantage of the external power supply, even though they give you a lot of cord, is that this mount will rotate around as it tracks. So it rotates in azimuth, which means it spins. That can end up taking this cord and wrapping it all the way around, and then you can end up tugging on things and breaking the connection. There is a feature in here, a cord wrap feature, so that the mount knows not to spin all the way around. So you can set that up as well, but you got to watch out for that. And make sure when you first turn this on that you are far enough forward with your imaging train. Use the hand control to slowly bring this down and make sure you clear, because you don't want to inadvertently bang into this and break something. So we have it leveled. We're going to put the power in. Then we'll go into the hand control, and you can find all this in the instructions. You set the date, time, location, daylight savings versus standard time. Make sure all that is correct. And then we'll do, I like to do the 3-star alignment. There are several different alignment routines. There's the 1-star, 2-star, there's the solar system alignment, but the one I like is the 3-star alignment. And why do I like that? Because I can get pretty good go-to capability. It will put things in the field of view pretty much every time. And all I have to do is pick 3 bright objects in the sky. I don't even have to know what stars they are, or they could even be planets. You could even use the moon, but I would suggest you try to concentrate on stars. You'll be a little more accurate since the moon is so big. So you pick 3 stars, widely separated in the sky, one by one, and you will center it in the eyepiece, or in this case, we'll center it in the field of view of the camera, and then we'll let it know it's aligned to that star, and then we'll bring it off to a star in another part of the sky. So I like to do 2 in one side of the meridian, but spaced apart, and then go swing over to the other side of the meridian and do another one. And the only requirement they give is that the 3 stars not be in a line. If they're in a straight line, you won't get an accurate alignment. So when you've done the 3rd star and you say you're aligned, it will think about it, it'll process it, and it will come back and say success, and it will even tell you which stars those were. So it's nice to check and say, oh yeah, that's what those 3 stars. Sometimes it will fail, and then you just repeat the process a little more carefully, or select some stars that are in different positions. And I haven't had any trouble making that work. So that's what I mean when I say these things are very easy to set up. There is no polar alignment. This cannot be polar aligned. You don't need to worry about that. The 3-star alignment gives you go-to alignment, and it will enable this thing to track an object in the center for a fairly long time. But as I said, objects on the perimeter of the field of view, if your exposure is too long, they'll appear to rotate about the center. All right, the sun is just setting, waiting for it to get a little bit darker. I have finished the setup here. You'll see I have the USB cable connected to the camera. I have a little strain relief here, and then the cable will hang from there. I just have to be careful as I'm doing the 3-star alignment. When I do a star in this direction, I may have to move the laptop with me around so the cable doesn't drag on the scope. I'm powering everything with my Jackery 500, so I have the output, DC output to the mount, and I'm using the AC output to my laptop. And I've already pre-configured, so this stuff is all in the manual. The objective of this video is not to go through all the manual settings, but make sure, as I said before, that you have the time, location set correctly, daylight savings or not, and that way when you do the alignment and you ask to go to a particular deep sky object, it will put it in the field of view. Also, I don't have a dew shield for this, which would be nice. Right now there's not much humidity, so I'm not worried about it. I borrowed this from my astronomy club, and so there wasn't a dew shield that came with it. But we'll be okay without that, especially since we're out here at a dark site. So now all I have to do is wait for it to get dark enough to begin to do the 3-star alignment. I will use, this is a red dot finder, use the red dot finder to zero in on the star, and then it should be in the field of view of the camera once you have this aligned to the optical axis of the scope. And you can do that ahead of time by looking at some distant object in the daylight and making sure it's in the field of view of the camera, and then adjusting this so it's in the center of that. You can also, sometimes I do it on the moon if it's out of whack and it's late and I don't have anything, I couldn't do it during the day. All right, so let's just wait for the 3-star alignment and we'll get started. Okay, it's gotten dark enough that I can see a bunch of stars in the sky, and it's cooled down as well. So we're going to start the alignment procedure. When you turn on the mount, it'll tell you the procedure for going through the align. We're going to use Sky Align, which is the 3-star alignment. The really nice thing about that is you don't even have to know which stars are which. So if you're a beginner and you don't know the night sky very well, that's fine. You just point to 3 bright objects spread out across the sky, align to them, and you're in good shape. It'll even tell you what those stars are after it does the alignment. We will first use the red dot finder to center it, and then we'll switch to centering it in the camera, and for that we're using the SharpCap. Now I've set the exposure and the gain a little bit on the high side so it will be very obvious, and then we'll kind of have to tone that down to center it, and we will use the crosshair function on the screen so we can find the center point. So it can be a little bit tricky in the beginning because the star is moving across the screen and you got to hurry to catch it when it crosses through the center of the crosshairs. So let me first get it into the red dot finder. I'm going to be looking at Sirius, so I'm already pointing in that direction. I'm pretty close already. Using the hand control. Okay, and then I can see it on the screen now. So we'll go to the screen. Now the trick is to keep this in the field of view while you do the alignment. So there's the crosshairs, and I'm going to drop down the motor speed. Make an adjustment here as it goes through. A little too far over a little bit. Oh, overshot. Okay. There it goes. And then I'll be ready to hit a line as it goes through there. So that's the first star aligned. And now we're going to proceed the same way for the next stars. Okay, for the second star, I'm going to use Betelgeuse. Okay, once again hit enter. Then the motor speed comes down. And we want to hit a line when it passes through the center. There we go. And now we're going to go to the third star, which is going to be on the other side of the sky. So we're going to pick a star in the Big Dipper. All right, now we're going to go around to the other side, facing north. And we're going to pick a star in the Big Dipper. And the same procedure, center it in the red dot finder, press enter, and then center it in the camera, press a line. All right. Okay, there we go. Centered in the finder. Okay, there we go. Close enough. And now it's thinking, it's calculating, and we're good to go. For the alignment, I was using a very short exposure. So now I've set the gain to 200, and let's bring the exposure up 6 seconds, and let's see what we get. Okay, so now you can sort of see there's something there. Let's increase the exposure. Let's go up to 10 seconds and raise the gain to 300. Since we've got dark skies, we can handle some high gain. Give it a minute to refresh. Now you start to see a lot more. And these are just live images, one after the other. Each image is refreshing. We're not doing any stacking at the moment. So we can go even higher in gain. Let's go to 400. Let's give it a full cycle to have an impact. Now you see quite a bit. You can see a lot of structure in the nebula. I mean, that's something you won't see in an eyepiece, which is why people do EAA. So we're really just looking at this thing at 10 seconds and see what we're able to get. And so it's tracking pretty well, and it put that almost in the center of the field of view, which was the objective of the 3-star alignment. Now we can push the exposure even higher. Let's go to 20 seconds. Now the Orion Nebula is a difficult one because it's so bright that the core gets blown out when you try to bring out the nebulosity on the outer edges. So you need a real high dynamic range for that. All right, and now we see a lot more of the nebulosity. Now we're seeing some star trails. There was a little bit of wind. Let's let this refresh and see. And you see the star trails are all going in the same direction. Yeah, there you go. Now stars are getting a bit to be more round. So a little bit of burst of wind or something. And I told you, it's not the sturdiest way I have it attached, but it works pretty well. So the Orion Nebula is a pretty easy one because it's very big and bright and beautiful. Let's try another object. Let's go to the Cigar Nebula M82. Okay, so here's M82, and it actually put it in the center of the field of view. So as I said, that 3-star alignment is actually pretty good. Now we can do things like zoom in. Let's go to 100%. And there you can see it. And you see a lot of noise in the background. It's because we have high gain and short exposures. There's not a lot of data, but you can clearly see the Cigar Galaxy. Now, this is not meant to be a SharpCap tutorial. There are plenty of tutorials online. In fact, I'll post a link at the end of the video to a nice written tutorial on High Point Scientific's website, but you can find them on the SharpCap website and so forth. Let me bring this back down. The objective of this video is just to give you an idea of what you can see with EAA and a SCT on an alt-az mount. And you can clearly see we're getting some pretty nice stuff. Now, I'm not doing dark frame subtraction. I'm not doing bias frames or flat frames. Those can all improve the quality of the image, and those are also done on the fly. So let's try to do some live stacking here. Now what it's going to do is it's going to take images and it's going to capture, and in the lower left corner it says 1 frame, and in the lower right corner is the frame counter. And so it's going to stack additional frames one on top of the other. And there went the second one. This is a histogram. And this shows the curve, the light of the different colors, red, green, and blue. And I'm going to reset this histogram because it was stretched. And stretched means we've brought the black point up to the, there, let me bring this black point up to this point. So when it's down here, the background is kind of bright. When you bring it up here, it darkens. If you go too far, you're going to lose some of the data. So you got to be careful about that. And here's the midpoint. This is the grayscale. This can bring up more, but it can also bring out the background more. And so we've stacked 4 images, a total of 79 seconds. And as time goes by, we see more and more detail on these images. So that's the beauty of live stacking. And you can let this go for many, many minutes and things will continue to improve. Now, the biggest improvement to this background would be dark frame subtraction. And all you do there is cover the scope, tell it to take a dark frame. You take the dark frame with the same settings that you're taking these light frames. It will make an average master out of those, and it'll subtract the background noise, because there's always background noise in these cameras. Hot pixels, warm pixels, and so forth. So we've done 2 minutes and 10 seconds, and you can see quite a bit here. And then you can also do an auto stretch, this button over here. It does the stretch what it thinks is the ideal. I don't really like that stretch. Sometimes it's better, sometimes it's not. Let's go back to reset and bring the black scale up. I want to bring it up too far. At the base of that curve. And that's probably okay. All right, so that's an example of what you can get with a galaxy like the Cigar Galaxy M82. And you can clearly see the structure in here, which makes it famous. You're not going to see these red jets coming off of it here that you see in a Hubble Space Telescope picture. You'd have to do a really good astro image to get that. You won't get that by just doing what we're doing here, but it's clearly you can see the galaxy and the galaxy structure. So let's try one more Galaxy M51. So I'll stop this live stack and we'll move on. So let's pause this thing. All right, so we're back to live view. I used the live view button up there. We have the same exposure of 20 seconds, and I have the gain up pretty high, 400. That's why the background is so noisy. We can drop that down. So there you see, we're right in the center. So it's amazing, 3-star alignment. Does such a great job. So let me drop the gain down. Maybe that'll help with the background noise. I'll drop it down to 300. Now, a lot of people like to take very short exposures. Let's just try this one at the 20 seconds and do the live stack. Turn on live stacking. We have to clear. And we'll reset the histogram, and then the counter is in the lower right hand corner again, and there is the first image. So you see the one galaxy and the other galaxy. You can start to see some of the spiral arms. Let's zoom in here, go to 100. And recenter this. There's 2 frames. And let's just let this run for a little while. All right, we have 4 frames stack. I'm going to manually adjust the histogram, bring the black level up, and do some gray scale stretching. You're starting to see a little bit more. To 50%. So we see the full screen here. Now you can clearly see the arms on the galaxy. And we're at 2 minutes and 22 seconds. Okay, we've been stacking now for 4 minutes, and you can see the image is getting to have more and more detail. The background is becoming more uniform. There are some striations there. Again, doing a dark subtraction would help a lot with the background. And you can even do the flat frames to help with the variation of light across the optical path, although it doesn't look too bad here. So you can do the same thing with very short exposures, 5 seconds or so. And you see, this is not having too much difficulty stacking these because we're looking pretty much north, and we can do fairly long exposures there without seeing any star trailing. Now what happens with each successive frame is not exactly lined up with the original frame, so when they stack them, you'll start to see a black border around the edges. And that black border is indicative of each frame being offset, rotated, and shifted a little bit from the previous, because after all, we're on an Alt-Az, not an equatorial mount. But it's not too bad when we're looking in this direction. So that's a quick demo of what you can see with an 8-inch Celestron SCT on a very simple Alt-Az mount, using a very simple 3-star alignment, no polar alignment, just a basic go-to alignment, and a program like SharpCap. There are other programs that you could use. SharpCap there's a free version which has all of the features I just showed you and more. I'll put a link to Robin's website. There's a more sophisticated version that has all kinds of great features once you learn and master the simple ones. And that's for a modest price. I forget what he charges for that, but it isn't much. So if you enjoyed this video, please press the like button. If you would like to see more of my videos, you could subscribe. And I encourage you to visit my website, californiaskies.com, where you will find more articles, reviews, tips, equipment discussions and some of my EAA images and some of my astrophotography images where I'm beginning to do astrophotography. So thank you for tuning in, and I hope this helped you.